Hi everyone. So today we're going to talk about fluid dynamics and continuity. All right, so the past couple lessons we've talked about hydrostatics, and that's dealing with fluids that are not moving. And now we're going to be dealing with dynamics, which is movement due to forces. Specifically, if you remember from Physics 1, dynamics is the study of motion under forces. So the objective here is to apply conservation of mass to fluids, and the reason this is important is because physics is based upon several conservation laws. That's one of the fundamental things in physics is conservation, right? So we have conservation energy, conservation of momentum, conservation of arguably mass. I say arguably because it's essentially the same thing as conservation of energy. And we also have conservation of charge. Right? So those are the four of the fundamental conservation laws. And so today we're going to apply conservation of mass to the idea of fluids, specifically fluids that are moving. But first I just want to explain what an ideal fluid is, or if you hear this term ideal fluid, what does it mean? So the first thing is that this fluid is incompressible. That is that you cannot change its density. Number two is that the flow is steady. That is so that the velocity of fluid at every single part of the fluid is going to be constant. And we can kind of see this if we draw what are called streamlines. So this kind of image here shows you that. We have what's called laminar flow and turbulent flow going on. So laminar flow we see here with the lines around whatever this object is that's creating this, that's disrupting this fluid. And in these linear parts here are laminar flow. That's where the flow is steady. So this fluid in this picture and the lines might be behaving ideally. Or we could have turbulent flow. You can see here that with that cloudiness, that kind of those eddies, so to speak. Here the velocity is not constant, so that fluid there is not an ideal fluid in that area. We also want the fluid to be non-viscous if we're dealing with an ideal fluid. Viscosity is resistance to flow, so non-viscous fluids mean that we're not dealing with any friction. So in all these situations here, we're dealing with ideal fluids. We also have this quantity called mass flow rate. I apologize for this image being kind of blurry, but let's suppose, so basically today we're going to actually be interested in what happens to a fluid when it's compressed or decompressed, I guess is the opposite of compressed. So if we have some sort of tube and the tube gets squeezed and becomes a smaller tube, or gets big and becomes a wider tube. So the situation we're analyzing right up here, up top, is actually a fluid in a large tube moving into a smaller tube. So we can analyze the mass flow rate here. So we're going to define mass flow rate as the amount of mass, delta M, of that fluid that passes in a given point per unit time, delta T. And we'll have this given point be the cross-sectional area. So in this diagram here, those cross-sectional areas we label with A1, A2, A1 being in the large area of the tube, A2 being the small area of the tube. And we'll assume these fluids are moving at two different speeds, or later on we'll see they have to be. But the speed in region 1 is going to be velocity 1. Or V1 I should say, and the speed in region 2 we'll label as V2. So mass flow rate we'll say is delta M over delta T, change in mass over change in time. Now the volume of fluid that's passing through region 1, so i.e. area A1, in a given time is going to be, so we can express that as a mathematical expression. Volume is going to be an area times the length. So if the fluid moves from one point to another, that change of difference, we multiply it by the cross-sectional area, we get the amount of the volume of the fluid. And we have the same situation for region 2. Now the mass flow rate here We can rewrite in terms of density if we'd like to, since we know density is mass over volume. Therefore, the change in mass is going to be the density of the fluid times the change in volume. So that's how you get that second equation, so to speak, I have there. And we can rewrite that in terms of area and length. And then we can see, if we apply what we know from kinematics, that velocity is going to be length over time. We see that we can rewrite this mass flow rate as an expression in terms of density, cross-sectional area, and the speed of the fluid. Now this is going to be useful, so we can write a similar expression here for the second region of the tube, where we get density of the fluid in region 2 times the area in region 2 times the velocity in region 2. We can then come up with an equation of continuity. So what continuity basically says is, so continuity means the same, right? So here we're dealing with the same amount of matter, same amount of mass, since we're dealing with an ideal fluid. It's incompressible. So if we're dealing with some sort of tube, so here I have the same diagram, but drawn a little bit differently. So if we're dealing with some sort of tube here, and you have some volume of liquid entering the tube here to the left, then we're going to have that same amount of liquid exiting on the right. So those cross-section cylinders there are the same volume. They're different widths because the areas are different, the cross-sectional areas, but they're the same amount of volume. And that's where the key here is. So the equation of continuity, we start with the statement that the volumes are going to be the same. So therefore, the amount of mass traveling through those have to be the same. Right? So that's where this central statement I have here is. And the one thing we can say is, since we're dealing with an ideal fluid, its density is not going to change because it's incompressible. So those two density values are actually the same density and cancel out. So we're left with this bottom squared equation here, is that the cross-sectional area in region 1 of the tube times the speed of the fluid in region 1 is going to be equal to the cross-sectional area in region 2 times the speed of the fluid in region 2. This is how the continuity equation is presented on your formula sheet. Please note that this is, in essence, a conservation law. It comes from conservation of mass. Now, another thing to note here is just analyzing this formula. So the mathematical product of area 1 times speed 1 is going to be a constant value. So therefore, if we increase the area, we see that the speed in that area, the speed of the fluid, is going to have to decrease. Right, so that means that regions of a tube that are going to be the larger region, the speed of the fluid is going to be slower. Conversely, if the area decreases, then speed has to increase. So therefore, regions of the tube that are squeezed to be smaller are going to move faster. That's basically what I have here in that box. I also want to mention we could also write this continuity equation in terms, you might see this letter Q thrown around here and there. Q is used to symbolize volume flow rate, so we could rewrite this velocity times area as a volume flow rate. Volume flow rate is just delta V over delta T. We can kind of get that expression from the formulas before. Both of these expressions of the volume flow rate are going to be useful. So you can either express the continuity equation in terms of velocity and area, which is how the AP exam does it, but you can also express it in terms of delta V over delta T, so the change in volume over that time interval. Both are going to be extremely useful, though just note that the AP formula sheet only presents one of those. So you're going to have to realize that the continuity equation, that's just conservation of flow rate, conservation of mass, so it's equivalent to saying it's the change in volume over that time interval that the volume's changed. We can see continuity in real life. For example, if you were watering some flowers at home using a hose, if you don't have any nozzle on the hose, the water just kind of pours out. But if you put a nozzle on the hose, right, the area, cross-sectional area of the hose then decreases in size, and you see the water shoots out at a much faster velocity. Okay, so that's just this continuity equation working in the real world. You can also see it with when you turn on a faucet. If you notice when you turn on a faucet, right, you can do this at home right now if you'd like, you'll see that the water stream actually gets thinner as you go down. The reason for this is if you analyze just one molecule of water there, as the water molecule falls, it's actually accelerating. And as it's accelerating means it's moving faster the further down the stream it is. As we just learned, if it's moving faster, the cross-sectional area has to be smaller. So that's why the stream of water then tapers. So we can go through a couple examples here. So the speed of water through a hose. So let's suppose we have a garden hose and has an inside diameter of 16 millimeters. And the hose can fill a 10-liter bucket in 20 seconds. Okay, so we want to find first the speed of the water out of the end of the hose. And then second, we want to find what diameter nozzle would cause the water to exit with a speed 4 times greater than the speed inside the house. Right. So I have here my work for this problem. So if you looked on the left here, in the top left, I have my diagram. So we have a hose, and it's shooting out water that fills a bucket. Right? Not very exciting in my diagram. I also listed what we know. So we know the diameter is 16 millimeters, which then is the same thing as saying our radius is 0.008 meters. So notice I am converting to SI units. The volume of the bucket's 10 liters. I did not do this conversion here, but if you see my note on the bottom of the left column here, 1 liter is the same thing as 10 to the negative 3 meters cubed. So later on I will need to convert that 10 liters to meters cubed. The time we have is 20 seconds. That's fine and dandy. That's in SI units. And we're looking for the speed of the hose. So the one thing I have to be careful with here in looking at my notes is that I use the lowercase v for speed and the uppercase v for volume. So in part A, we're just applying the continuity equation. So the volume flow rate coming through the hose is going to be the volume flow rate entering the bucket. So in looking at what information was given to us in the problem, it's going to be most useful to express the volume flow rate for the hose in terms of the cross-sectional area of the hose times the speed of the water exiting a hose. The reason why we want to do that is because we know we have the radius, so we can easily find the area, and we want to find that speed. That VH is what we're looking for. Now, and for the bucket, we're given the volume of the bucket. It's going to be more useful to express the volume flow rate of the bucket in terms of volume over time. Right? So that's what I've done here. So there I just now am rearranging for the speed of the water exiting the hose, and I replace the area of the hose with pi r squared. Right? And when I plug in all the numbers there, I get a speed of 2.5 meters per second. All right, part B then asks, what diameter of nozzle would cause the water exit with a speed 4 times greater than the speed inside the hose? This is just analyzing the relationship between the quantities. Right? So since we know that the volume flow rate has to be constant, then if we have to increase the speed by a factor of 4, that means that the area must decrease by a factor of 4. In order to do that, and looking at the area formula, area is going to be equal to pi times r squared, where that r is diameter over 2. So therefore, whatever we do to the diameter, we're going to have to square that quantity. So for example, if we were to half the diameter, that would cause it to change by a factor of 1/4, which is exactly what we want. Right? And I kind of show that more mathematically here in the third column, part B. Right, so in doing that, we know that we have to have half the diameter, and then we get that 8 millimeters. All right, so I hope that was helpful.